everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to know what the term buffer solution means, and then to understand the action of it, and then we'll be able to calculate the pH of a buffer solution given appropriate data, and calculate the concentrations of solutions required to prepare a buffer solution of a given pH. Buffers are solutions which resist change in pH when small amounts of acid or alkali are added, and there are two types of buffers. The first is an acidic buffer, and these are made by mixing weak acids with their corresponding soluble salt, and basic buffers, which are made by mixing weak bases and their corresponding soluble salt. So we'll be going more in depth into these two types of buffers. So firstly, we're going to look at an acidic buffer. And so this is when you add a weak acid with a salt corresponding to it, a soluble one. So Na plus salts are always soluble. So an acidic buffer maintains a pH below 7, and so this means that acidic buffers always have acidic pHs. So how do they maintain their pH? Well, consider this equation. So here we have the dissociation of an acid, HA, into its associated ions, H plus and A minus. An acidic buffer contains a very soluble salt of the acid, and this dissolves in water to form a large concentration of the H plus and the A minus ions. And so first, looking at when we add an alkali to the buffer, what happens is that the OH minus, which has been added because it's part of the alkali, so if we had sodium hydroxide, that would be the alkali, and OH minus would come with that. And that OH minus reacts with the weak acid, and this forms A minus and water. And so this means that the concentration of HA decreases and the concentration of A minus increases. And because of this actually removes the added OH minus. The pH will remain constant. If you add an acid to the buffer, what happens is that the H plus that's come from the acid can react with the A minus, which is from the weak acid in the buffer, and this forms more undissociated acid. However, there's only a very, very small amount of this A minus present from the weak acid that we've got in the buffer, but we do have a very, very large supply from the soluble salt because the soluble salt fully dissociates. And so the A minus from the soluble salt, eventually when the A minus from the weak acid has all been used up, then reacts with the H plus from the added acid. So the A minus is from the soluble salt, and this forms more undissociated acid, HA. So in conclusion, we have that the weak acid component in the buffer acts as a source of this undissociated acid, which can remove any added OH minus ions, so when you add an alkali. And it does this by this equation of undissociated acid plus the OH minus of the alkali forms A minus ions and water. And the salt component of the buffer acts as a source of A minus ions, which can remove any added H plus, so any added acid. And the A minus reacts with the H plus to form more undissociated acid. So another way in which we can make an acidic buffer, so achieving a mixture of a weak acid and its salts, is by neutralizing some of the weak acid with an alkali. So for example, sodium hydroxide. So if we had ethanoic acid and added some sodium hydroxide to it, then what would be formed would be this salt and water. And so this could act also as an acidic buffer, as we have an acid and its salt. If we neutralize half the acid, we end up with a buffer with the pH equal to its pKa value. And this is because it has an equal supply of HA and A minus. And this is a very useful kind of buffer because it is equally efficient at resisting a change in pH when an acid or an alkali is added. A basic buffer is one which can maintain a constant pH of above 7, so it'll always have an alkaline pH. And basic buffers can be made out of a mixture of aqueous ammonia and ammonium chloride. So when we add an alkali, how it maintains a constant pH is that the ammonium ion reacts with the extra added OH minus from the alkali, and this forms the ammonia and water. And what happens when we add an acid is that the ammonia reacts with the added H plus from the acid, and so the ammonia reacts with H plus to form the ammonium ion. So now we're going to talk about how to find the pH of buffers. So we're going to look at this example. A buffer consists of 0.1 moles per decimeters cubed of ethanoic acid and 0.1 moles per decimeters cubed of the salt. The Ka for ethanoic acid is 1.7 times 10 to the minus 5 moles per decimeters cubed. The pKa is 4.77. So what is the pH of the buffer? And so first what we do is write out the equation for the Ka. And so Ka will be equal to the concentration of this CH3COO minus ion multiplied by the concentration of this H plus ion and divided by the concentration of the ethanoic acid. Because the ethanoic acid dissociates in an equilibrium to this H plus and this CH3COO minus ion, and we find the Ka from this. And we know that this is all equal to 1.7 times 10 to the minus 5, which is given in the question. And then we can sub in the numbers for the concentration of the salt and the concentration of the acid because it's given in the question to us. And so first I'm just going to rearrange this equation to have H plus, or the concentration of H plus as the subject. So we have the concentration of H plus is equal to Ka multiplied by the concentration of the ethanoic acid divided by the concentration of the salt, the negative salt. And so we get 1.7 times 10 to the minus 5 times 0.100 over 0.100. So this gives us 1.7 times 10 to the minus 5 moles per decimeters cubed for the concentration of H plus ions. And then we use the formula for pH. So pH equals the minus log to the base 10 of this concentration of H plus ions. And so that equals minus log to the base 10 of 1.7 times 10 to the minus 5. And this gives us a pH of 4.77. Another calculation that we can do is finding the pH of an acidic buffer by adding sodium hydroxide to a weak acid. So we're going to look at this example of calculate the pH of the buffer formed when 500 centimeters cubed of 0.4 moles per decimeters cubed of sodium hydroxide is added to 500 centimeters cubed of 1 mole per decimeters cubed of the weak acid HA. And the Ka value is given to us as 6.25 times 10 to the minus 5 moles per decimeters cubed. So the first thing I'm going to do is find the moles of sodium hydroxide we have and find the moles of the weak acid HA that we have. So I'm going to use the equation moles equals concentration times by the volume. So we have that the moles of sodium hydroxide is equal to 500 times 10 to the minus 3 because we need to convert the centimeters cubed to decimeters cubed, and multiplied by 0.400, and that gives us 0.2 moles. And then I do the same thing for the moles of this HA, and we have 500 times 10 to the minus 3 times by 1.00, and that gives us 0.5 moles. And now the next thing I do is write out the equation of the reaction that's happening. So we have a weak acid, HA, and this is reacting with a strong base, which is sodium hydroxide, and this goes to form the salt, NaA, plus water. And so from this equation, we can see that it's a one-to-one relationship between the weak acid and the sodium hydroxide. And so we have two different scenarios. The first scenario is if we use 0.2 moles of sodium hydroxide. So if we use 0.2 moles of sodium hydroxide, that will react with 0.2 moles of this weak acid HA. And our second scenario is if we use 0.5 moles of HA. So if we use 0.5 moles of the weak acid, this will react with 0.5 moles of sodium hydroxide, and that's because of that 1-to-1 ratio. And so we can see from this that this second scenario can't happen because we don't have enough of the sodium hydroxide. And so that means that the first scenario happens. And so we have some HA in excess after everything's reacted because we're only reacting 0.2 moles of it. And so what we get is the HA in excess is equal to 0.5, which is how many moles we have, minus 0.2, which is how many moles we're reacting with the sodium hydroxide, which equals 0.3 moles. And we also know that there's a 1-to-1 ratio between the sodium hydroxide and the salt NaA that we produce as well. So we know that if we are reacting 0.2 moles of sodium hydroxide with 0.2 moles of HA, it will produce 0.2 moles of this salt NaA. So we've got NaA produced is equal to 0.2 moles. And then what we can do is we can work out the weak acid, the concentration of the weak acid. So we have the concentration of the weak acid is equal to this 0.3 divided by the total volume of the reactants. And so because we have 500 centimeters cubed of the weak acid and 500 centimeters cubed of the sodium hydroxide, we must have 500 times 10 to the minus 3 plus 500 times 10 to the minus 3 as the total volume. And so this equals 0.3 moles per decimeters cubed. And then we could also do the same thing with the A- ions, because the A- ions come from this salt, NaA. And so the concentration of A- ions is equal to 0.2 over the same total volume. So the 500 times 10 to the minus 3 plus 500 times 10 to the minus 3. And that equals 0.2 moles per decimeters cubed. And now we can use our Ka equation. So we've got Ka equals the H plus the concentration of it multiplied by the concentration of A minus divided by the concentration of HA. And so now we can start subbing in values. But first I'm going to rearrange so that we've got the concentration of H plus as the subject. So we have the concentration of H plus is equal to Ka multiplied by the concentration of HA divided by the concentration of A minus. And so the Ka at the start was 6.25 times 10 to the minus 5. So we've got concentration of H plus equals 6.25 times 10 to the minus 5 times by concentration of HA, which is 0.3. And divided by the concentration of A minus, which is 0.2. So that gives us 9.375 times 10 to the minus 5. And now we can use our pH formula to find the pH. So we have pH is equal to minus log to the base 10 of this concentration of H plus ions. So we have minus log to the base 10 of 9.375 times 10 to the minus 5, and this gives us a pH of 4.03. So now we're going to look at calculating the pH of a buffer after acid has been added to it. So we're going to look at this example. We have 1 decimeters cubed of a buffer solution of ethanoic acid at 0.1 moles per decimeters cubed and sodium ethanoate at a concentration of 0.1 moles per decimeters cubed. The Ka value is 1.7 times 10 to the minus 5 moles per decimeters cubed. And if we add 10 centimeters cubed of 1 mole per decimeters cubed of hydrochloric acid, calculate the pH. So the first thing we do is work out the number of moles of the hydrochloric acid that we've added. And this will be equal to the concentration multiplied by the volume. So we've got concentration is 1.0 times by 10 centimeters cubed. So we need to convert that to decimeters cubed. So we divide it by 1,000 or times 10 to the minus 3. And that gives us 0.01 moles. And this actually tells us how much H plus is added because HCl is monoprotic. So 1 mole of this HCl will donate 1 mole of the H pluses. And so this also comes out to be the moles of H plus ions added. And now we have to think about what actually happens when we add an acid to an acidic buffer. So what happens is that the ethanoic ions, the negative ions, will react with the incoming H pluses, so the added H pluses from the hydrochloric acid. And this will form some more of the undissociated acid, so the ethanoic acid. So what we get is that these ethanoate ions react with this surplus of H plus that we have now that we've added acid. And this forms some more of the undissociated acid, which is ethanoic acid. And so we can see from this that the concentration overall of this ethanoate will decrease and the concentration overall of this ethanoic acid will increase because we're producing more of it by reacting this ethanoate with the H plus which has been added. So now we can use this to help us in calculating the pH. So the next thing we do is calculate the initial moles of ethanoic acid. So initial moles ethanoic acid, and we use the concentration times volume again. So we've got 1 decimeters cubed of a buffer solution at 0.1 moles per decimeters cubed. So that means we have 0.10 times by 1.0, which is equal to 0.10 moles. Now, we've also worked out that the moles of H plus added is 0.01 moles. And now we look at the stuff in blue. So we've worked out that the concentration of ethanoic acid should increase from start to finish by adding this acid. And so that means that the new moles of ethanoic acid will be bigger than the initial moles of ethanoic acid. And so we can work out the new moles of ethanoic acid by taking the initial, so 0.10, and adding on the moles of H plus added. Because looking at the blue equation, it's a 1-to-1 ratio between this H plus and the ethanoic acid. So if we're adding 0.01 moles of H plus, that means we're forming 0.01 moles more of this ethanoic acid. And so the new moles of ethanoic acid that we have is 0.11 moles. And now we can work out the concentration of, the new concentration of the ethanoic acid. And so we have concentration of ethanoic acid, moles equals concentration times by volume. So concentration must be equal to moles divided by volume. And then we have 0.11, and then we put this over the volume of the entire buffer. So the volume of the buffer was 1 decimeters cubed from the question. So we put it over 1, and then we get 0.11 moles per decimeters cubed. And now we go through the same process, but with the ethanoate. And so what we have is initial moles of this ethanoate is equal to the concentration times by the volume in the question. So we have 1 decimeters cubed, so we use the whole buffer solution, this 1 decimeters cubed, and also 0.1 moles per decimeters cubed as the concentration. So we have 0.10 times by 1.0 is equal to 0.10 moles. And now we look back to the blue equation again. So we know that the overall concentration of this ethanoate will decrease. And that means that we need to take away the moles of H plus added to find the new moles of this ethanoate. So the new moles of ethanoate, so because the moles will decrease from the initial to the new, because it's reacting with the added acid to maintain a constant pH for the buffer. So that means that the new moles of ethanoate will be 0.10 minus the moles of H plus that we've added, because again it's a 1-to-1 ratio, and so we get 0.09 moles. And again we then work out the concentration of the ethanoate ion. So we've got the concentration of ethanoate is equal to 0.09, which is the moles, and divided by the total volume, which is the volume of the buffer. So that will be 1.0. And so we have 0.09 moles per decimeters cubed. And now we use our Ka formula with these values to work out the concentration of H plus ions and then eventually the pH. So we have that Ka is equal to H plus multiplied by this ethanoate divided by ethanoic acid. And so now we can put in our values for ethanoic acid and ethanoate and Ka to find the H plus. So rearranging this, we get concentration of H plus is equal to Ka multiplied by the concentration of ethanoic acid. They're all divided by the concentration of the ethanoate ion. And we were told at the start of the question that the Ka is equal to 1.7 times 10 to the minus 5. And so the concentration of H plus is equal to 1.7 times 10 to the minus 5 multiplied by the concentration of ethanoic acid, which came out to be 0.11, and divided by the concentration of ethanoate, which is 0.09. And so this gives us 2.08 times 10 to the minus 5 moles per decimeters cubed. And then finally, we use the pH formula to find the pH. So we have pH is equal to minus log to the base 10 of the concentration of H plus ions. So we have minus log to the base 10 of 2.08 times 10 to the minus 5, and this comes out to be 4.68. So as you can see, the pH should still be acidic because acidic buffers will always maintain an acidic pH. So now we're going to look at calculating the pH of a buffer, but this time when an alkali is added to it. So for this example, we have 1 decimeters cubed of a buffer solution of ethanoic acid at 0.1 moles per decimeters cubed and sodium ethanoate at a concentration of 0.1 moles per decimeters cubed. The Ka value is 1.7 times 10 to the minus 5 moles per decimeters cubed. And if we add 10 centimeters cubed of 1 mole per decimeters cubed of sodium hydroxide, calculate the pH. So again, the first thing we do is calculate the number of moles of sodium hydroxide that we're adding. So the moles of sodium hydroxide added is equal to 1.0 times 10 times 10 to the minus 3, because we're converting the centimeters cubed into decimeters cubed, and this gives us 0.01 moles. So now we have to think about what happens when we add an alkali to a buffer. So what happens is that the NaOH, so the alkali, sodium hydroxide, will react with the unassociated acid, ethanoic acid, to form more of the sodium ethanoate and some water. So we have that sodium hydroxide, which is being added, reacts with ethanoic acid to form this salt and also water. And so we can see from this that overall the concentration of ethanoic acid will decrease because we're reacting it with all the sodium hydroxide that has been added. And also the concentration of this ethanoate ion will increase because we're producing it from reacting the ethanoic acid with the sodium hydroxide. And so this is going to help us with working out what happens to the pH. And so the next thing we do is work out the original moles of the ethanoic acid that we have. So original moles of ethanoic acid, and that'll be equal to the concentration times by the volume. So we have 0.10 times by 1.0. 1.0 is the volume of the entire buffer solution, which is the one we want. And this comes out to be 0.10 moles. And then we look back to the blue equation and we think, what happens to this ethanoic acid? And we know that the overall concentration has to decrease. And that means that the overall moles has to decrease from original to new. So we have the new moles of CH3COOH after the alkali is added, and this will come out to be the original moles, so 0.10, minus the moles of sodium hydroxide which has been added. So minus 0.01, and this gives us 0.09 moles. And now we can work out the concentration after the alkali has been added of this ethanoic acid. So we've got the concentration equal to the moles over the volume, and this equals 0.09 over the volume of the entire buffer, so the 1.0 decimeters cubed, and this gives us 0.09 moles per decimeters cubed. And then what we do next is we do the same thing with the ethanoate. So we have the original moles of the ethanoate, and in the question it was given to us as 0.10 moles per decimeters cubed, and the volume was 1 again. So we have 0.10 times 1.0 is 0.10 moles. And now again we think back to the blue equation, and we know that this concentration of the ethanoate ion will increase from original to new. So that means that the moles will increase. And so we can work out the new moles of ethanoate. And this will be equal to the original moles plus the sodium hydroxide which has been added, which is the 0.01. And so this gives us 0.11 moles. And again, we can work out the concentration of ethanoic acid, and we get the concentration of ethanoic acid is equal to the moles divided by the volume. So we have 0.11 divided by the volume of the whole buffer solution, which is 1 decimeters cubed. and so we get 0.11 moles per decimeters cubed. Now we use the Ka equation. So we have Ka is equal to the concentration of H plus multiplied by the concentration of ethanoate, or divided by the concentration of ethanoic acid. And so rearranging this, we can find the concentration of H plus to find the pH. So we have Ka multiplied by the concentration of ethanoic acid divided by the concentration of ethanoate. And so what we get is H plus is equal to Ka, which was 1.7 times 10 to the minus 5, and this is multiplied by the concentration of ethanoic acid, which was 0.09. And then on the bottom we have the concentration of ethanoate, which is here, so that's 0.11. And this gives us 1.39 times 10 to the minus 5 moles per decimeters cubed. And then finally, we use the pH formula to find the pH. So we get pH is equal to minus log to the base 10 of concentration of H plus ions, which equals minus log to the base 10 of 1.39 times 10 to the minus 5, which is equal to 4.86. So again, we can see that the pH has remained in the acidic region because it's an acidic buffer, so the pH will always be acidic. So now we're going to move on to some questions. The first question is, what is the pH of a buffer which has been made by adding 100 centimeters cubed of 0.5 moles per decimeters cubed of ClCH2COOH to 100 centimeters cubed of 0.250 moles per decimeters cubed of sodium hydroxide? And we've been given the pKa value of the chloroethanoic acid. And so what we do first is work with the pKa. So we have the formula pKa is equal to minus log to the base 10 of Ka. And so to find the value of Ka, we then do 10 to the power of minus pKa. And so we have that Ka is equal to 10 to the power of minus 2.86, which is equal to 1.38 times 10 to the minus 3 moles per decimeters cubed. And then what we think about is we think about the equation. So first let's write it out. We have the chloroethanoic acid reacting with sodium hydroxide. And so what this will form will be this salt and also water. And so we can find out the moles of the acid and the moles of the alkali added, and then see how much is left of the acid. So we have the moles of this chloroethanoic acid is equal to concentration times volume. So we've got concentration of 0.500, and we've got a volume of 100 times 10 to the minus 3 decimeters cubed, and this comes out to be 0.05 moles. And then the moles of sodium hydroxide that we react this with is equal to 0.250 multiplied by 100 times 10 to the minus 3, and this is equal to 0.025 moles. And now when we look back at the equation, we see that there's a 1-to-1 ratio between the chloroethanoic acid and the sodium hydroxide. And this means that we can either have two scenarios. So the first scenario is that we have 0.05 moles of this chloroethanoic acid reacting with 0.05 moles of the sodium hydroxide, or we have that 0.025 moles of sodium hydroxide react with 0.025 moles of this chloroethanoic acid. And now we can see that only one of these can happen because we don't have enough of the sodium hydroxide for the first reaction to happen. So we must have this second scenario here. And so we have some of the H plus spare. We have some of this chloroethanoic acid spare because only 0.025 moles of it react, but we have 0.05 moles of it. So we have that the moles of this chloroethanoic acid left is equal to 0.05 minus 0.025, and this equals 0.025 moles. And now what we can do is we can use the Ka formula. So we have Ka is equal to ClCH2COO minus, so this is how it dissociates in water, and then this is all over the chloroethanoic acid. And then now what we can do is we can work out the concentration of H plus because we've got everything now. So the Ka value we worked out as 1.38 times 10 to the minus 3. So we have H plus concentration is equal to 1.38 times 10 to the minus 3. Multiplied by the concentration of ethanoic acid, which is this 0.025. But then you have to put it over the volume of the buffer. And so the total volume of the buffer we have is we're adding 100 centimeters cubed to another 100 centimeters cubed. That means that the total is 200 centimeters cubed. So we have 200 times 10 to the minus 3. And this is over the concentration of the ClCH2COO minus ion. And so the concentration of that is equal also to 0.025 because we see from the equation that it's a 1-to-1 ratio between the sodium hydroxide and this ion. So if we're using up 0.025 moles of sodium hydroxide, then we must be forming 0.025 moles of this ion. And so again, we get 0.025 divided by 200 times 10 to the minus 3. So actually for this question, the volume wasn't needed because it cancels out. And so this gives us 1.38 times 10 to the minus 3 moles per decimeters cubed. And now we use the pH formula. So we have pH is equal to minus log of the concentration of H plus ions, which is equal to minus log space 10 of 1.38 times 10 to the minus 3, which is equal to 2.86. So before I move on to the second question, feel free to click off and try it for yourself first. So for A, calculate the pH of 0.2 moles per decimeters cubed of ethanoic acid after 0.1 moles per decimeters cubed of sodium ethanoate was added. And so what they're actually doing is they're trying to create a buffer. So first of all, what we do is work out the concentration of ethanoate added. So the concentration of ethanoate added is actually equal to the concentration of sodium ethanoate added. And this is because every sodium ethanoate has one ethanoate ion. And so we know that the concentration of sodium ethanoate added is equal to this 0.100 moles per decimeters cubed. So now what we do is we look at the Ka. So we have that the Ka is equal to the concentration of H plus ions multiplied by the concentration of these ethanoate ions over the concentration of ethanoic acid. And because we know the Ka value, the concentration of the ethanoic acid and the concentration of ethanoate, that means we can work out the concentration of H plus ions by doing the concentration is equal to Ka multiplied by the concentration of ethanoic acid, or divided by the concentration of this ethanoate ion. And so now we just put the numbers in. So we have the concentration of H plus is equal to 1.8 times 10 to the minus 5 multiplied by the 0.20, and this is over 0.100, and this gives us 3.6 times 10 to the minus 5 moles per decimeters cubed. And then what we do is we use the pH equation. So we have pH is equal to minus log to the base 10 of the concentration of H plus ions, which is equal to minus log to the base 10 of 3.6 times 10 to the minus 5, and this comes out to be 4.44. So for part B, if 0.01 moles per decimeters cubed of hydrochloric acid is added, what is the new pH? So now I have to think about what happens when we add an acid to an acidic buffer. So what happens is that the H plus ions which are added, so they come from this HCl, they react with the ethanoate ions, so the CH3COO minus ions. And so what we get is we get H plus CH3COO minus goes to form more of the undissociated acid, ethanoic acid. And so what we can see from this is that the concentration of this ethanoate will decrease because we're using it up to get rid of the H plus ions which have been added by the hydrochloric acid, and the concentration of ethanoic acid will increase because we're forming more of it. And so now what we do is we calculate the original moles that we have of everything. So the original moles of this ethanoate is equal to 0.100. Because no volumes are given, we can just assume that everything is in a decimeters cubed, because it'll just cancel out anyway. And so we have 0.100 as the moles, and then we have the original moles of the ethanoic acid, and this is equal to 0.20 moles. And now we work out the number of moles of HCl added. So we've got that the moles of HCl added is equal to 0.010, and this is actually equal to the moles of H plus added. And this is because HCl is monoprotic or monobasic, so each HCl has one H plus ion. And so now we look back at the logic that we looked at before of how the concentration of the ethanoate decreases and the concentration of ethanoic acid increases. And so we can work out the new moles of ethanoate and ethanoic acid. So we have that the new moles of ethanoate acid, we know that this has to decrease because the overall concentration decreases. And so we have the original moles, 0.100 minus the moles of H plus added, which is 0.010. And so what we get is 0.09 moles. And then we do the same for the ethanoic acid. So we've got new moles of ethanoic acid is equal to the original. And this time we're adding the moles of H plus added because the concentration overall of the ethanoic acid will increase. And so we get 0.21 moles. And now what we do is we use the Ka formula. So we have that Ka is equal to concentration of H plus over the concentration of CH3CO minus divided by the concentration of ethanoic acid. And so rearranging this, we can find the concentration of H plus ions. And we get concentration of H plus ions is equal to Ka multiplied by the concentration of this ethanoic acid divided by the concentration of the ethanoate ion. And so what we do now is put all the numbers in. So we've got the concentration of H plus, and Ka value in the question was 1.8 times 10 to the minus 5. So we have 1.8 times 10 to the minus 5 times by the concentration of the ethanoic acid, which would be 0.21. We don't need to put in, we don't need to convert it to concentration because the volume we have for the ethanoic acid and the volume we have for the ethanoate will be the same, so they'll just cancel. So we divide that by the 0.09, and this gives us 4.2 times 10 to the minus 5 moles per decimeters cubed. And then the very last step is to use the pH formula. So we have pH equals minus log to the base 10 of the concentration of H plus ions. And so we have minus log to the base 10 of 4.2 times 10 to the minus 5. And this equals 4.38. Hi everyone, thank you so much for joining this video. We're going to look at some harder questions on the topic of buffers. So for this question, the acid dissociation constant Ka for a weak acid HX has a value of 4.83 times 10 to the minus 5 moles per decimeters cubed at 25 degrees Celsius. And a solution of HX has a pH of 2.48. For A, calculate the concentration of HX in the solution. So what we do is we have to use this pH formula that we have. So we have pH is equal to minus log to the base 10 of the concentration of H plus ions. And so to find the concentration of H plus ions, we need to do 10 to the power of minus pH. And so the concentration of H plus ions in this case is 10 to the minus 2.48. And this is equal to 3.31 times 10 to the minus 3 moles per decimeters cubed. And now we write down the equation for Ka. So we know that Ka is equal to this concentration of H plus multiplied by the concentration of X minus and divided by the concentration of HX. But we know that because it's a weak acid, it doesn't dissociate very much, and so the concentrations at equilibrium of the H plus and the X minus are actually the same. And so we can write this as the concentration of H plus squared over the concentration of HX. And by rearranging this, we can then find the concentration of HX. So we have the concentration of HX is equal to the concentration of H plus squared over Ka, which is equal to 3.31 times 10 to the minus 3 squared, all over 4.85 times 10 to the minus 5, and this equals 0.227 moles per decimeters cubed. And so this is the concentration of HX at equilibrium. But for a weak acid, we can actually assume that the concentration of HX at equilibrium is the same as the concentration of HX initially. And then for part B, the acid dissociation constant Ka for the weak acid Ha has a value 1.35 times 10 to the minus 5 moles per decimeters cubed, and a buffer solution was prepared by dissolving 0.0236 moles of the salt NaY in 50 centimeters cubed of a 0.428 moles per decimeters cubed solution of the weak acid HY. Calculate the pH of this buffer solution. Well, the first thing we would do would be to calculate the moles that we have of the weak acid HY. So the moles of HY is equal to concentration times volume. So we have 0.428 multiplied by 50 centimeters cubed. So we need to divide that by 1,000. And that gives us 0.0214 moles. And now we can construct a Ka formula. So we have Ka is equal to the concentration H plus multiplied by the concentration of Y minus over the concentration of HY. And so rearranging this, we can find the concentration of H plus, which is equal to Ka multiplied by concentration of HY over the concentration of Y minus. And so what we do now is we do concentration of H plus is equal to Ka, which is 1.35 times 10 to the minus multiplied by the moles that we found of the HY, because there's no point of using the concentration because we're going to use the moles for the NaY for the bottom of the equation anyway, so the volume would just cancel out. And so we're going to put in the moles of HY, which would be 0.0214. And then this is all over the 0.0236 because the Y minus comes from the salt, NaY. And then this gives us 1.22 times 10 to the minus 5 moles per decimeters cubed. And then we use the pH formula that we have. So pH is equal to minus log to the base 10 of concentration of H plus ions, which is equal to the minus log to the base 10 of 1.22 times 10 to the minus 5, which is equal to 4.91. And now for C, a 5 times 10 to the minus 4 mole sample of sodium hydroxide was added to this buffer solution. Calculate the pH of the buffer solution after the sodium hydroxide was added. So from part B, we found that the moles of HY at the start was 0.0214. And we also know that the moles of Y minus is 0.0236, that it's given in the question. And so now we think about what happens when we add an alkali to an acidic buffer. And what happens is that the alkali being added, the sodium hydroxide, is going to react with some of the undissociated acid, so the HY in this case. And this is going to form NaY, the salt, and water. And so this forms more of this Y minus. And so we can see from this equation that the concentration of HY will decrease because we're using it up to get rid of the extra OH minus ions added with the alkali. And the concentration of Y minus will increase because we're producing more of it. And so now we know, we have an idea of what's going on, we can start to put in some numbers. So we have the original moles of HY here, and so we can work out the new moles of HY. So the new moles of HY will be equal to the old moles, so the original, so it's 0.0214, and then we'll have to minus the amount of sodium hydroxide added, because we can see that the concentration of HY will decrease overall. So first we need to work out the moles of sodium hydroxide which was added, and it's given to us in the question actually. So 5 times 10 to minus 4, So we minus 5 times 10 to the minus 4, and this gives us 0.0209. We do the same thing with the y minus. So new moles of y minus is equal to 0.0236, but this time we add the 5 times 10 to the minus 4 because the overall concentration of the y minus increases. So the overall moles of y minus must increase. And this gives us 0.0241. And now we use the Ka formula again. So we have the Ka is equal to the H plus concentration multiplied by the Y minus concentration over the concentration of HY. And so to find the concentration of H plus, we must do Ka multiplied by concentration of HY over the concentration of Y minus. And so we have that the concentration of H plus is equal to the Ka, which was equal to 1.35 times 10 to the minus 5, multiplied by this the new moles of the HY here. We don't have to use concentration because it's the same volume, so they cancel. So you have 0.0209 and then divided by the 0.0241. And this gives us 1.17 times 10 to the minus 5 moles per decimeters cubed. And so now that we've got that, the final step is to use the pH formula. So we have pH is equal to minus log to the base 10 of concentration of H plus ions. So you have minus log to the base 10 of 1.17 times 10 to the minus 5, and this gives us a pH of 4.93. So as you can see, the pH hasn't changed very much from before we added the sodium hydroxide, and this is the whole point of buffers, because they maintain their pH, so it's maintained an acidic pH.